Hi, welcome back to our Fundamentals of Optical Spectroscopy short course. This is part 3, Equipment for Optical Spectroscopy. So first, a short introduction, and I do want to keep it short. This is episode 3, and I'm hoping that you've watched the other 2, so you already hopefully know who I am and who we are. If not, welcome to Andor. It was established in 1989 as a spin-off of Queen's University, the physics department specifically, I think. And our headquarters is in Belfast, although we have R&D and sales offices all over the world. We have about 360 or so employees, and most importantly, we are a leader in scientific imaging, spectroscopy, microscopy systems, and analysis software. And we've been part of the Oxford Instruments Group since 2014, so about 8 years now. So what do we actually make? Well, most relevant to our discussion today, we make spectrometers. And here you can see these are the boxes. Here's one attached to a microscope, a number of cameras for spectroscopy, and you can see these laid out here, and a number of cameras that are primarily used for low light imaging on telescopes, microscopes, optical systems of this nature. We also make optical cryostats, and you can see here's an Optistat dry, and these are meant for cooling samples down to liquid nitrogen or liquid helium temperatures, and still being able to access them optically. And we also make, although I'm clipping part of the image, confocal microscope systems. So here is a dragonfly, and I'm clipping the image a little bit, but you can see it here. So who am I? I feel like you've probably already heard me talking for potentially hours before, but I'm Adam Wise, one of the applications field specialists at Andor. So what I do specifically is work with scientists and engineers to find the equipment that will solve the problem or achieve the experiment and measurement that they have. I remember, I think these were used in the promo for this course, and here's me with some different goats. Here's a Nubian and a Saanen, and they're both goats, but they're very different looking. You can see there's a tremendous amount of goat diversity out there. Enough about the goats. I'm based in Philadelphia, and I've worked at Andor I'm in my 5th year here. Today we're going to be talking about equipment for spectroscopy. So specifically, and this is a bit simplified, that's going to be a spectrometer or a monochromator. They're often synonymous, but we'll talk about terminology a bit later. Basic design, like what's actually inside the box. Dispersion, how colors are separated. Spectral resolution, how you quantify how well colors are separated, and how you otherwise quantify spectrometer performance. We'll also talk about detectors, so single versus multi-channel, what that means, and some key performance parameters like quantum efficiency, noise, and pixel size. So as a reminder, a spectrometer or a spectrograph or spectroscope, and those are more or less synonymous, although I feel like you hear them less nowadays, mostly spectrometer here, separates light or electromagnetic radiation for measurement. It usually spatially separates colors, although there are other strategies like interferometric methods or filters or so on. For example, FTIR, and I don't have the bandwidth today to talk about that. And what it needs to do is control incoming light, have something to disperse or separate the colors, something to measure the light, optics to move everything around to get light from one place to another, and motors to potentially move or automate everything, all of those things. Optional but really helpful, and some reference or standard for wavelength calibration. So here's a simple but illustrative spectrometer that you could potentially make in your own house. So although this is happening in the 18th century, all the parts are in place. There's an entrance slit, a little aperture here in a shutter that allows collimated, very parallel rays from the sun to come through, and not collimated or parallel, meaning they don't spread out as it propagates, so you can see it's like a pencil of light. There's a dispersive element, so something to separate the colors, which is a prism on a beautiful looking turned brass candlestick or something here. And our detector is simply a white screen that you look at. So dispersion, meaning colors being separated or being spread out, is happening in this direction vertically. And you can see red is ending up over here and purple over here. So you could easily set this up in your own house if you have a prism or buy one on Amazon or something. And although it's a few hundred years later, the more things change, the more they remain the same, if refined somewhat more. So here's a spectrometer that we sell now. This is a Chimera 328. And here's the entrance slit that meters the light coming through or reduces the light coming through to a defined area. Our dispersive element is a grading. I'll talk about those later if you're not familiar with the concept of a diffraction grading. And our detector, instead of being a white painted board in a drawing room, is a back illuminated high performance CCD camera. And we'll talk a little bit about cameras today, although I'm going to give it short shrift because it's such a wide and interesting topic. So I want to walk through an example of dispersion. So first let's talk about refraction by a prism. So we all hopefully remember Snell's law from high school or something, which is to say that it defines how light is bent going from a medium of one index of refraction to another index of refraction. So here's the indices of refraction, and these tell us how fast light propagates in a medium, how fast light goes in a medium, either air or glass. And in this example, I'm using a BK&N, a BK7 prism. That's a common crown glass type, and it's often the default for different optical analysis software, but it's just a very common borosilicate glass. So I have my algebra down here in my trigonometry, but basically if I hit it at such an angle, then I go through and I get bent towards the surface normal going in here, so I get bent towards a line that's right angled to the surface, and then I get bent the other way coming through here. So I'm not going to belabor this, it's all well and good, but I think we believe that light bends when it hits a piece of glass at an angle. However, I said index of refraction as if it's a constant, but the index of refraction, N, actually changes quite a bit as you change wavelength. So you can see this is the wavelength axis down here in microns. So 500 nanometers, 1000 nanometers, 1500. Our visible to near IR is going to be over here. And you can see that it goes from about 1.55 in the blue, a bit more maybe, down to 1.5 and change a little bit over 1.50 down here in the near IR. So why is that important? Because that angle through which the light bends is going to depend on wavelength. And here's another borosilicate glass that you may have seen. This is Pyrex. So one of the things that's nice about these is that they're quite thermally stable glasses. So Pyrex doesn't shatter when it gets hot, and that's why you use it. You can boil water in it without it cracking. So now we have two colors, and at these two different wavelengths, we'll have two slightly different refractive indices. And as a result, we'll get bent through two different angles. So this is where the dispersion comes in. The dispersion meaning spreading light spatially by different wavelengths. So our red, or well, actually this is probably a little bit further than we can see, but it's near IR red light, is going to get bent through one angle, and our blue light is going to be bent through the other angle. I only showed two wavelengths here, but if we had a white light source out here coming through in a thin beam, we would get a little spectrum here. Now, I only showed the math here to show that at this particular configuration, the angle through which we're separated is quite small. So if this is coming out at 55.7 degrees, this is coming out at 53 degrees. So not a tremendous amount of dispersion. And sometimes we need quite a bit. So we need physical separation of our colors to measure them accurately. Why is that? Well, here's a spectrum that I showed 2 weeks ago, which is Joseph von Fraunhofer's 1815 sketch, or etching, I should say, of the solar spectrum. So here's what it originally looks like in his publication here. And you can see that this is a broad spectrum that has a number, hundreds of individual absorption lines that you copied down. And you can only see those absorption lines because the spectrum is quite wide. It's got significant dispersion. However, if you squeeze that same image down into about a tenth of the dispersion, or a tenth of this physical separation, we can't really see those lines anymore because they've simply been squeezed together where we don't have sufficient detail. Our eyes can't resolve them anymore. So in our last example, the separation is about 2.5 degrees. We could raise that a bit, and I have some bonus questions here if you want to go back and figure out using some calculus what the optimal angle is for separation. And a question of would it pay to switch to a higher dispersion glass, because there are many, many types of glass, and BK7 is just one. So if we wanted to get that whole visible spectrum using that kind of dispersion, it would only, if we wanted to get it to be about an inch wide, 2.5 centimeters, we need a 60 centimeter throw. So that's just to get that whole visible spectrum to about this big. We're going to have to squint very closely at it on our little screen to see it. So even to get that small that small width, we need about a half a meter. So we have a fairly large box at that point. And if we wanted to go further, we need to get a bigger and bigger room. So you can see back in that previous slide where it showed the spectrum with Isaac Newton, he's using the whole room to project that spectrum simply to get a big enough spectrum to look at. He has pretty small angular dispersion there. So again, why does that matter? Physically separating colors well is one of the key ingredients in spectral resolution. Spectral resolution meaning how well can our spectrometer take two very, very similar colors, two very, very close colors in wavelength, and separate them and measure one from the other. So 400 nanometers to 800 nanometers in my example is a very big wavelength range, hundreds of nanometers. What if we're looking for something small, like a Raman shift of 30 nanometers, which is about 1,000 wave numbers in the green? Or in some cases, we may want to measure really small shifts, like sub-nanometer, maybe picometer. So less than a nanometer, never mind hundreds of nanometers. So let's go into a bit more depth on spectral resolution. So again, spectral resolution is how well your spectrometer and detector, working in concert, can separately measure two very close wavelengths. So here's our light source, and imagine our light source is sending out exactly two colors. So it's not a big, broad white light. It's putting out exactly two wavelengths, lambda 1 and lambda 2, which in this case will be 650 and 450. So very red light and very blue light. Here's our imagination spectrometer for this model, and it's not 100% accurate for sure, but it's got all the same features. So there's an entrance slit or a little board with a small hole here. And because we're sitting pretty far away from the light, any light that makes it through this hole is going to be pretty well collimated or pretty narrow. It won't spread out very much once it comes through here. The light hits our dispersive element, and one wavelength gets bent up this way, and one wavelength gets bent down this way. And we have our detector, piece of paper, film, camera, doesn't really matter right now. We're just trying to see whether we can actually tell these dots apart. It doesn't matter how we do it, or these little images that are copies of the entrance port here. So with two very different wavelengths that are a few hundred nanometers apart, we can resolve that pretty well because they get spread out pretty well. We can see this blob here and this blob here, no problem. However, as the wavelengths get closer, so say 450 and 550, because these are a little bit closer together in wavelength, they're not going to disperse quite as far from each other with the same setup here. And they're going to start to merge a little bit. At this point, we can still see them separately. They're not overlapping yet. Until eventually, with a small enough separation in wavelength, and here it's just 1 nanometer at this point, those spots are going to merge to the point or overlap to the point where we can't resolve them separately anymore. And that's going to be a function of how much we're dispersing, how well we can see, and how well our spectrometer forms these little images here, these little circles that are kind of copies of the light coming through here, or the shape of the light coming through here. So at this point with our imagination spectrometer, we can't resolve those because they're overlapped. But just a note, so 1 nanometer is not that small. So for example, our Chimera 328i could have a spectral resolution of 0.05 nanometers. So a small fraction of a nanometer. I'm just using in 1 nanometer as a small example for this prism spectrometer. So what could we do about it if we wanted more spectral resolution? Well, the simplest, or maybe the easiest to draw anyway, is to make the box bigger. So remember, Isaac Newton was using his whole room to get a large throw or a wide spectrum from a small angle. So here's our angle, which is still the same, but simply by making the box bigger on our imagination spectrometer, which is easy to change by dragging a box around in PowerPoint, harder to do in real life, we can get a larger throw here. So even with the same wavelength difference, 1 nanometer, now our spots are going to be further apart on our spectrum, so we can actually see them again. That will eventually stop working. So you will either get an impractically big spectrometer, or you'll get beaten by diffraction, because these will get spread out bigger and bigger as they come through this aperture, and eventually you'll get to the point where they get super fuzzy. But that's just one option, and it actually works in real life, making a bigger box, but has diminishing returns. Another thing we can do is make the little hole that I'm letting light in through smaller. So if we make the hole smaller, because our rays are coming through parallel here, our spots get smaller. So this is basically more or less the idea behind the spectrometer entrance slit. And here you can see this one is the side on the side of a chimera, or the entrance port of a chimera spectrometer. And you can see if you take that cover off, it's two little jaws that are opposed to each other that we can open and close to make basically the hole in front of the spectrometer bigger or smaller. That eventually stops working as well, because at a certain point when you make that hole quite small, then diffraction becomes more and more of a problem. And we'll talk more about diffraction later if you're not familiar with it, but simply light coming through a small hole spreads out like ripples in a pond. It would be even better if we could just increase the dispersion that we have in the first place. So if we could just make this angle wider, then we'd have better separation on our two colored spots, and 1 nanometer, instead of being butted up against each other and merging, a 1 nanometer difference would give us two nicely resolved separated spots. So we could either switch our prism to something that disperses colors more widely, has more dispersion, and it can be harder to switch to a different prism, although it's possible as well. Prisms are limited by the material properties that they have, which is to say that if you remember that chart of index of refraction, I would have to find just the right prism material where our prism or our refractive index was changing faster, but in a way that wouldn't cause other problems. So prisms have their downsides. They're dependent on that unique set of properties with that particular glass or material. So let's bring in a different dispersive element, the diffraction grading. So this is the origin of the diffraction grading, which I thought was an interesting story. So around 1785, a Philadelphia man, and I couldn't find a picture of the actual guy, so here's Grady, who's a mascot in Philadelphia here where I live, notices a rainbow while looking through a silk handkerchief at a streetlight. So he's just minding his own business, looks through a handkerchief that's stretched tightly, and sees some interesting optical phenomenon. So as one does, he writes to a locally prominent astronomer, David Rittenhouse, who's born in the beginning or the first third of the 18th century. And inspired, Rittenhouse reproduces this effect by making a more controlled grading, which consists of hairs, or a hair perhaps, a very long one, strung between two fine screws. So it looks something like this. I keep having to position things because my head is blocking images in the corner. But imagine two finely threaded screws with a hair moving between, or hair going back and forth between them, and the spaces in between those hairs allowing light to pass. So unlike prisms, which spread light through different refraction for different wavelengths, diffraction gratings work by diffraction. So you might remember from high school physics or college that when you have a small slit and you shine a light through there, the different parts of the slit, or the different little subsections of the slit, are emitting light separately and give you kind of an interference pattern away from the slit. So here's what it looks like, and I can't recommend enough to go check out the Falstad applet about 2D waves. But if you have your light here, your slit here, you get this diffraction pattern. This is what it looks like in side view. You can't see this very well unless you were to hold up a sheet kind of 90 degrees to the slit here. But typically what you would see far off is this diffraction pattern. So this is from a single slit. Is viewed on a far wall with monochromatic light, and you have the central order here and little side lobes, separate orders here. So why do we care about this? Because these angles are dependent on wavelength. So if you bring more than one color in here into this and shine through this slit, you'll have angular separation on the different colors. A single slit is not very efficient, but we can create an array of slits. So here's 3, and that's a start, but eventually we'd want thousands and thousands of these slits working in concert. And by doing that, we can create a situation where we're going to diffract light of different wavelengths in different directions, and that will give us our dispersion. So we keep adding more and more slits until we have a whole array. And here's a kid's toy educational diffraction grading, and you can see looking through this diffraction grading at a light, we have our little spectrum. And if you were to zoom in there, you'd see lots and lots of parallel lines that are acting like slits. The great part about diffraction gratings is that they can either work in reflection or in transmission. So we can shine light through, or we can bounce light off and get diffraction and get dispersion. So here's the grading equation, the equation that describes how this diffraction takes place. And here are the parameters that it depends on. So what we really care about is we have some incident beam here, and what we want to know is for a particular wavelength, how is that light going to get diffracted? What angle is it going to come out with? We want a particular angle because we want maybe some particular spectral resolution. So we want either a very high angle to give us high dispersion, or a low angle if we want a really wide bandwidth. So here's what that angle depends on. So this angle being sine theta or theta d here, the angle of diffraction. So first there's an order. Let's ignore it for the moment, pretend it's 1. Our wavelength, so it's going to be proportional to wavelength, and our grading groove spacing. So how narrowly spaced those grading, the grooves in our grading is, the slits on our grading. So let's step through the grading equation in a little more detail here to get a better understanding of why diffraction gratings are so great and why we use them much more often than prisms, or one of the reasons why we use them more often than prisms in spectrometers. So the grading equation, the order times the wavelength of light, is equal to the groove spacing of our grading times the sum of the sine of the incident angle and sine of the diffracted angle. So for simplicity, let's try to take out as much as we can from this equation and simplify it. So let's imagine that the light hits the grating straight on. That is to say, the incident angle is 0, and n, the order, is 1, because it usually is for most things. So it's first order diffraction. So that simplifies this to the wavelength equals the groove spacing times the sine of the angle of diffraction. Now, if we want to solve for just the angle of diffraction, which is what we're usually after, then that turns into arc sine, wavelength over groove spacing, equals the angle of diffraction. So arc sine, again, it just looks like this. It sounds fancy, but arc sine, if you increase this, the arc sine goes up. If you decrease what's in here, the arc sine goes down. So why is this interesting? So here's our angle of diffraction, and that's what we want to occasionally change, right? If we want more or less spectral resolution. So if we change our groove spacing, then we change our angle. So that's the cool part. We get a simple relationship describing dispersion. No messing around with different classes, and we can make it more or less by simply scratching or etching different numbers of lines on our gratings. So either tightly spaced lines or less tightly spaced lines. So now we've redesigned our imagination spectrometer into a simple grading spectrometer. If we want more dispersion, then we change or we replace our diffraction grading with one with more lines per millimeter, more dense lines, so tighter slit spacing. If we want smaller spots, we can adjust our entrance slit to a point. Otherwise, we're going to get beaten by diffraction, a different type of diffraction here. Our size of the box is still fixed, but we can build different size boxes. And you can see above me, I have to keep changing some of these images because my head is here. But we have at the top a 1/3 meter box, the Chimera 328, so about 1/3 of a meter in size. A Shamrock 500, which is a 1/2 meter box about in size, and a Shamrock 750, which is a 3/4 meter box. So that's talking about the focal length of a mirror, which is a bit different, but it gives you more or less the size of the box. And our dispersion for the same grading is about proportional to that size. So we are taking the strategy of building different size boxes. There's more to it, but that's also a big part of it. And just to note, one of the main things that we're skipping over, that I'm skipping over, is that in our imagination spectrometers or in Isaac Newton's whole room spectrometer, they're using, or we're using, a very narrow beam of light. So we're using whatever kind of gets through right along the optical axis here, and then that gets diffracted here into 2 different wavelengths. So if we did that in real life, or if that was how our spectrometers really worked, they would be incredibly inefficient because we would only use the tiny little ray of light that comes in along this optical axis here. Real spectrometers, like our Cherney-Turner designs, and this is a diagram here at right of what that means, collect a wide cone of light from the entrance and refocus it onto the detector. So this is that cone of light here, and it goes onto a collimating mirror that turns that cone parallel, makes those rays parallel. That gets diffracted onto a focus mirror, and then that focus mirror focuses these images of the entrance slit here onto the detector, onto the camera. So real spectrometers like ours collect light much more efficiently, but then have to focus it, so there are some focusing optics in here. And as a result, imaging performance is also part of the spectral resolution, and hopefully we'll have more time to talk about that. We'll see how it goes. But I don't want you to think that the Cherney-Turner design is the only spectrometer design that there is. I think it's the most popular or the most common, but there are other alternatives that are trying to solve different problems and do different things. So for example, Shell spectrometers like the Michel 5000 that we make combine high spectral resolution with very wide wavelength range. Normally with the Cherney-Turners, that is mutually exclusive, and you can think about it in terms of if we have very high dispersion to get two wavelengths far apart from each other, then we're not going to be able to fit a very wide wavelength range in one space on one sensor. However, what Shell spectrometers do is they have two dispersive elements. So the Michel uses a prism and a grating. We've talked about both of those. And they're kind of turned at 90 degrees to each other. So one disperses in the Y direction and one disperses in the X direction. So rather than getting one spectrum across the sensor, we get something like a page in a book where there's a row that continues and continues and continues, kind of in a spiral down the page here, or down the sensor. So this Shellogram lets you capture a tremendous amount of information in one shot. So this is very popular for things like optical emission spectroscopy and LIBS, where you're going to get a large, wide spectrum that has lots of information in very many narrow peaks. So that brings us to the subject of detectors. So now that we've gone through the trouble of creating a high resolution, high spectral resolution spectrometer, how do we record these spectra that we're making? So typically everything that we do is going to involve converting light to electrical charge. In the past, photographic film was used, less so nowadays, but in some labs you can still see dark rooms that aren't usually used for anything but storage nowadays, but we're an integral part of the measurement process. Mostly photographic film is gone at this point. We always want, however, regardless of the detector, high sensitivity, meaning we want to detect a small amount of light sensitively. We want high spatial resolution, so we want to know where our light is coming in on a detector and landing. And we want high dynamic range, so we want to be able to measure small signals and big signals in the same measurement. And for some applications, we also need high time resolution. I won't have too much time to talk about that today, but that's an important part as well. So for detectors, there's one quick distinction I want to make. There are point detectors like photodiodes, photomultiplier tubes, and APDs. They're point detectors because they have one photosensitive element, so they have one pixel. We're a bit spoiled nowadays because oftentimes, or almost always, we're using array detectors. So CCDs, EMCCDs, ICCDs, CMOS, and SCMOS cameras. So they have a large number of photosensitive elements or pixels. So a 2D array, although you can't see the individual elements here, there are millions or at least thousands of them, generally millions, megapixels. So point detectors are still great for many important applications because they have high speed. If you want to know about some light being absorbed as quickly as possible, low latency. Oftentimes they have low noise, but they are oftentimes low quantum efficiency, which I'll talk about in a second. Many of them have excellent quantum efficiency, so that's not always true. But they are just one piece of information. You can't form an image or even a spectrum with them in one shot. So how do you get a spectrum out of a point detector? Well, you've got to move something. You have your spectrum in space and you have your point detector as just one little piece. So generally that will involve moving the grating to send one wavelength at a time. On the other hand, array detectors are like the cameras that you have and are used to in life. They take photos, or they take at least strips of information at one time. So they are oftentimes higher sensitivity. You're getting a lot of information in one shot, and they can be extremely low noise. Historically, they're much slower, if only because you have to get the information from millions of pixels, but they're getting faster and faster. They are quite fast. Historically, they also have lower dynamic range, and we'll talk about that a bit. But when I'm saying detector, you can kind of assume, at least for the purposes of this presentation, that means an array detector, a camera. So we certainly want our detector to be sensitive so that it can measure small signals. So how do we describe a sensitive detector? Well, first we need a high quantum efficiency, which is to say the probability that a photon is converted into an electron. So quantitatively, if we have 100 photons in and we get 95 electrons out, then we have a 95% quantum efficiency, which is really good and actually pretty achievable. The second is we need low noise. So if we have a lot of noise, we won't be able to measure small signals, because here you can see we have a small signal and it's almost lost in the noise. So the higher the noise, the more signal it's going to take to get something measurable and convincing that it's real. I have an interactive application note here. You can't click on it now, but you will when you see the slides, that talks about how we plot this and how we quantify this and what signal to noise plots mean, and how you can sort of quantitatively talk about what's the smallest signal that you can measure with a particular level of noise. So here are some representative quantum efficiency curves for detectors, mostly silicon based, in the UV to near IR. So one thing I want you to notice is that quantum efficiency isn't one number. It strongly depends on wavelength. So some of them might have low UV quantum efficiency, very strong visible quantum efficiency, and then lower near infrared quantum efficiency. So depending on the particular wavelength range that you want to use, you'll need to use a different sensor. So if you saw on the previous slide, I showed back illuminated versus front illuminated, with back illuminated being a lot more sensitive. So what that actually means, front illuminated is when you take your photosensitive substrate, your silicon wafer or whatever here, and you lay down your metal contacts, your metal wiring on top of that, and you block some of the light. Why would you want to do that? Well, that's kind of how you have to make them for the most part, in that you have a substrate and you're laying things down, electrically conducted things down on top of that. So you don't have much of a choice in the past. Nowadays, we can make back illuminated sensors where the photosensitive part is on top of the metal wiring, or at least in front of the metal wiring. And it's a lot more photosensitive because we're not putting down a bunch of things that are blocking our light sensitive part of the sensor. There's actually a weird parallel here. Vertebrate eyes are kind of front illuminated, where our support structures or our blood supply or whatever for the photosensitive part of the retina, that blocks the photosensitive part of the retina itself. Whereas cephalopod eyes are back illuminated, so their photosensitive parts are in front, not blocked by the support structures. So why is that? Why don't we have beautiful, more sensitive, potentially back illuminated eyes? I think just a quirk of evolution, unfortunately. Back illuminated is a lot more sensitive, but it's harder to make. So you have to jump through a bunch of hoops, basically turn your front illuminated sensor over, grind down the back until it's very, very thin, and then do additional processing on it. So it was a later engineering invention, but vastly preferable for the most part. So to give you an idea of the many options available for different sensors, here's a single spectroscopy camera that we make, the IDIS 420, this guy here, which is very popular. So you can see the quantum efficiency curves for different sensor variants, and they're all silicon. They're all, except for this one, back illuminated. So these are all different back illuminated sensors, but with different silicon types and anti-reflection coatings on top of the sensor, we can create a very different wavelength response. So here we have UV sensitive cameras, primarily visible, and then near IR. So these are the DDs for deep depletion. So these are a different type of silicon that gives you more near infrared sensitivity. But just within one particular camera, within one particular model, we can have very, very different sensitivity across wavelengths, or across different quantum efficiency across wavelengths. So there's quite a bit of diversity there. So you may have noticed with the previous quantum efficiency curves, and with all silicon sensors in general, the quantum efficiency starts to tail off or drop pretty heavily around a micron, give or take. So below that silicon band gap, which is to say at lower energies, other materials have to be used. So we would go from silicon to indium gallium arsenide, to lead sulfide, to indium antimonide, to mercad-tel out here for the really long wavelengths, the really low energies. So this is 1 micron, so we can't see anything beyond this. This is all infrared. And a note that I'm sorry for the units here. This is in specific detectivity instead of quantum efficiency, but the idea is the same in that more is more sensitive. However, if you're used to working with silicon sensors, these are all going to make you wish you were using silicon. So they get a lot less sensitive, a lot noisier. But you know, if you want to detect out here, what's your alternative, right? There are alternatives nowadays that I haven't gotten into for infrared detection with some superconducting detectors that I don't know enough to talk about, but I wish I did. Likewise, what if you want to go far above the visible in energy? Well, at higher energies, that is UV to X-rays, silicon actually works quite well as a detector. So here we have a bunch of different variants of high energy silicon detectors that are available for the ICON M-SO high energy detection camera. So you can see we no longer have a window here. We're just looking right at the sensor itself. We're not going to be limited by the transmission of whatever window material we might use over that sensor. So here's the near IR, the visible and the UV, and we can actually go with very high quantum efficiency off into the X-ray, into the hard X-rays. So through vacuum and extreme UV, all the way out to X-rays. So what makes for a sensitive detector? Well, noise, specifically the lack of noise. And the noise sources that we're talking about, there are quite a few, but most importantly are going to be read noise and maybe thermal or dark current noise. And we'll talk about that in more detail in a minute. So what exactly do we mean by noise and how can we quantify it? Well, noise is uncertainty about the real value of a measurement in one way of thinking. And we can either kind of talk about it spatially, where if we looked at a histogram of this patch that should be a uniform black color, there's some snow there. So if we looked at the distribution of brightness or the distribution of measurements in that across these pixels, we'd have some uncertainty about what the real value is. Or if we repeated the same measurement on one particular pixel, so if we were to just watch this pixel or watch this pixel, there is some underlying real brightness value probably that we're looking for, but we keep measuring, maybe it's a little higher, a little lower, a little higher, a little lower in some kind of unpredictable way. And that unpredictability is for us noise. So again, it's uncertainty about the real value of a measurement. Some forms of noise we can remove through very clever engineering. Some forms of noise are just part of nature and are inherently part of the measurement. So trying to figure out which is an important part of this process. So I briefly name dropped a couple of different types of noise sources a slide or two ago, but I wanted to go back and talk about two of them that are almost universal and have very different natures. So the first one is dark current. So this is a thermal false signal, thermally activated, that increases with integration time. So the longer your exposure, the longer your integration, the longer your measurement takes, you'll get proportionally more of this noise. On the other hand, readout noise is noise that occurs during digitization. So when we try to sort of weigh or measure the amount of charge in a particular pixel or particular part of the sensor. And that's fixed per measurement. So one of my old colleagues put it this way, that dark noise is the noise of the parking meter. And this is an analog parking meter that many of you are probably too young to remember. But you pay proportional to the amount of time that you're waiting there in the parking spot. So you get an amount of noise, an amount of dark current at a fixed temperature, at a particular temperature, proportional to the amount of time that measurement takes to do. On the other hand, read noise is a fixed cost, and this is the noise of an ATM surcharge. So whether you take out $20 or $100 or $1,000, depending on what your withdrawal limit is, you're going to get charged the same $2.50 here, but $3 or whatever. So this is the fixed cost or a per event, per measurement noise. Doesn't matter how long you expose for. And just to throw some numbers on here, so here's one of our common spectroscopic cameras, the ITIS 401. The actual magnitude of the dark noise is about 0.006 electrons per pixel per second. So not very much. We do very aggressive cooling on most of our cameras that really knocks down the dark noise. On the other hand, the read noise is about 8 electrons RMS. So one question I have as a bonus is, at what exposure time do these two noise sources become equal? And the answer may surprise you. Usually dark noise doesn't become a major issue until you have fairly long exposure times. Read noise is a major noise source, sometimes the major noise source. But we can do something about it with electron multiplying CCDs or EM-CCDs like this Ixon that we make. These use an on-chip charge multiplication mechanism to boost the signal before readout. So here's a schematic of the sensor in this camera. And once we convert the light into electrons, and these electrons are schematically indicated by these red dots here, we use the sort of the magic of compound interest and charge multiplication. By dropping these charges through a steep potential, we can multiply them and go 1 to 2 to 4 to 8 to 16 and so on. and get gains in the hundreds and overwhelm the read noise by just simply creating that much more charge before it's read out. So effectively lowering the read noise quite a bit. So you can see here, comparing an SCMOS and an EMCCD with just a few photons per pixel, we can massively drop the effective read noise in the background area here and get a much crisper, brighter image. So one more thing that goes into a sensitive, powerful detector is spatial resolution. So detector pixels have a finite size. Again, this is 2D arrays cameras. If those pixels are too big, we'll reduce our spectral resolution because we won't be able to resolve different peaks or different spots anymore. And you can see with my Mona Lisa here, I've chosen pixels that are too big, and although each pixel is going to collect a lot of light, through poor spatial resolution, I've reduced this to a pixelated mess. If those pixels are too small, on the other hand, they'll create unnecessary noise because they'll divide up that signal more than it needs to be. So actual pixel sizes or pitch range from about a micron in the iPhone, so for example in the iPhone camera, to 6 to 25 microns for scientific cameras or more. The optimal size, and there isn't one right size, it depends on the imaging system performance. So if your imaging system is creating spots that can only be so small, it doesn't make sense to use pixels that are smaller. What happens if our pixels are too big? Well, spatial and therefore spectral resolution are going to be limited to the pixel size. So here we have 4 pixels and we have a wavelength axis that we've calculated for this particular spectrometer geometry. So we have these overlarge pixels, we can illuminate them with a small spot. If we illuminate them here, the whole pixel lights up. The pixel can't tell which part was illuminated. So we're looking still and everything looks like it's been rounded basically to 440. So if we illuminate here, if we had smaller pixels, maybe we could pick that up. Here it's still going to look like 440. Likewise with this one. So basically we get kind of spatial rounding to the nearest pixel, or spectral rounding to the nearest pixel. It's a bit more complicated than that in the real world. The exact relationship between pixel size and resolution is complex. You can check out our resolution calculator to get kind of that math done for you. And on the other hand, your pixels can also be too small. So smaller pixels, the signal is divided further and further, while read noise, again, is per pixel. So we have our signal here that's being focused, we have an image that's being focused here, our spectral peak or our spectral point, and we have, only X number of photons illuminating this whole area. If we chop that up into finer and finer individual bins or individual pixels, then we're going to have smaller and smaller amounts of signal in each. And again, the signal's dropping, the noise is either increasing or staying the same depending on the mechanism. So we're going to get worse and worse signal to noise ratio. As well, smaller pixels physically can hold less charge, less electricity that light has been converted into. They have a lower capacity for holding charge, therefore a lower dynamic range. So we're not going to be able to measure the high highs and the low lows in the same exposure anymore. We're going to have a smaller dynamic range there. So what's the best pixel size? The best pixel size depends on the properties of the imaging system that we're talking about. So if we can form very, very tight, small peaks, then we're going to need proportionally small pixels to pick those up and map them accurately. If we're forming more blobby, looser shapes, then we're going to want big, physically large pixels to avoid oversampling and causing the problems that I just discussed with overly small pixels. Conclusions for today. Again, spectroscopy is just about separating and measuring wavelengths. So spectrometers typically use diffraction gratings to disperse those wavelengths, to disperse those colors and separate them and create a spectrum. Grading choice and spectrometer design, which we kind of went through a brief exercise on, determine dispersion. And a detector records the spectrum that we've created, ideally with zero noise and 100% detection efficiency, but in reality we have some trade-offs. Finally, next week, October 13th at 4 p.m. BST or 11 a.m. Eastern Time in the US, we have Pushing the Limits, Optical Spectroscopy at the Extremes, where Shane and I will review case studies of unusual, weird, impressive, and difficult spectroscopy experiments. So that's the next week. There is no beyond for this particular course because it's only 4 parts, but keep an eye on the Andor Learning Center for the next thing that we do and for all the other things that we've done. Thanks again for listening and for your patience through the first 3 parts of this, and I'll be answering questions now. All right, thanks again. Hey, so hopefully you can hear me. I need to apologize in advance for not posting the slides earlier for the first and third sessions, and I just sent those for posting to the Learning Center as quickly as possible. So they should be up pretty soon. If you can just go ahead and check our, again, Andor Learning Center, possibly early next week. And if you want to download a PDF version of the slides that you've seen for at least the first and the third episode of this short course. So as far as questions go, I'm just going to take a quick look. I don't have a tremendous amount of time to answer questions today, so I'm just going to do a few. And the one that I see that I'd love to answer is, do EMCCDs create artifacts during multiplication? I wouldn't say artifacts exactly. Artifacts to me sound like something specific that you're looking at that's a shape or a distortion. They do create additional noise, so multiplication noise, which I briefly showed for about 1 second on one of the slides. And that multiplication noise does increase the effective noise that you get. There are other more obscure artifacts that can happen as a result of charge shifting through the EMCCD gain registers, but there's no one EMCCD artifact that I would point to and say, oh, you're going to see a confusing fake feature due to just using an EMCCD. Man, I would love to do a whole presentation on imaging artifacts. Oh, that's just right up my alley, though. That's specifically the stuff that I love to talk about. So maybe that'll be the next time. I think we have, if you, again, not to name drop the Learning Center one more time, but if you look in the Learning Center on our Andor Learning Center site, we have a couple of articles about the finer points of EMCCD measurements. And I even have some YouTube videos up on that as well. But no specific artifacts does create additional multiplicative noise, or what's called like the excess noise factor, which is physically because the multiplication process is stochastic, that is to say random. So you have a random amount of gain. Basically, you don't know exactly how many electrons you get out when you put one in. On average, you do, but for a particular pixel, it's going to scatter around a mean value. So still useful for quantitative, but for quantitative measurements, it's not like it gives out a completely random number, but there's just some additional randomness injected there. And let's see what else. So I got another question about the quantum efficiency of photographic film, because I showed quantum efficiency curves for a fairly small number of detection, methods. I showed different types of cameras, and I am biased and blinkered towards just thinking about camera sensors and some single channel detectors that are kind of mainstream. But if you were to ask, what's the quantum efficiency of photographic film like they used to use? How much better is a scientific camera or a photomultiplier tube or whatever? And the answer is that photographic film emulsion the equivalent quantum efficiency is extremely hard to measure, because electrical measurements for fine amounts of charge or current are easier to do. How do you compare? You hook a wire up and you measure how many charges go through there. Easier said than done for sure, but definitely doable with a, you can go and buy a test and measure system that will measure nanoamps or picoamps or whatever. How do you do the same thing for photographic film? Well, I mean, it's not the same where it's creating an electrical current. There are electrons being moved by light. You are reducing, a silver halide grain or whatever into metallic silver. From what long story short, from what I understand, the quantum efficiency is really low. Definitely less than 10% likely. Again, there's lots of different types of photographic film, but less than 10% and probably more like 1% or less than 1% quantum efficiency or equivalent quantum efficiency. So it's not like you can use a trick and go back and use photographic film to get better efficiency. There's a reason that photographic film has been superseded completely. There aren't any throwbacks, and I say that there's always an exception, but
but people don't use photographic film anymore. Although it's beautiful, it's not sensitive, not as sensitive as a CCD or one of these scientific cameras. All right, so I apologize. I've rambled enough. I said I wasn't going to answer too many questions, but thank you again so much for your patience and your attendance. And I look forward to hopefully seeing you for the final part of this series, which will be next week, and that'll be Shane and I working together. And thanks again. Have a good weekend or Friday, and thanks again for listening.